Section 11.8, cylindrical and spherical coordinates. In section 11.7, we talked about quadric surfaces. 11.8 is going to continue that, but also introduce two new coordinate systems, so we'll have different looking equations and we'll be able to represent points in 3 space differently. The first type of coordinates that we're going to introduce are called cylindrical coordinates. All cylindrical coordinates is polar coordinates with an additional z to get into the third dimension. The same relationships hold as with polar coordinates. X is equal to r cos theta, y is r sine theta, r squared is equal to x squared plus y squared, and the tangent of theta is equal to y over x. Now, when you learned about polar coordinates, you didn't put any restrictions on r. R could be negative, and theta could go through any number of rotations. We're going to limit ourselves to make r greater than or equal to 0, and put theta in the range from 0 to 2 pi, not including 2 pi though. If we do this, this forces us to have a unique coordinate in cylindrical coordinates for all points in 3 space. So, most of this should be pretty simple. Like I said, it's really just polar with a z. So, I want to change this point from Cartesian to cylindrical coordinates. So the first thing I know is that r squared is equal to x squared plus y squared, or in other words, r squared is equal to 9 plus 9, which will mean that r is the square root of 18, or 3 square root 2. You don't necessarily need to simplify that, but it is 3 square root 2. Then I want to figure out what theta is. Now be careful here. It's always good to draw a picture. If I'm going through the point 3, 3, then theta is here. Theta is 45 degrees, or pi over 4. Make sure you draw a picture though, because of course I would get the same tangent value if I were in the third quadrant, but I would need theta to be, like for this, I would need 5 pi over 4. So I know r, I know theta, so then my cylindrical coordinates are theta z are 3 square root 2 pi over 4 and 5. I can do very similar things. If I have the point 2, 0, negative 1, I want to change that from Cartesian to cylindrical. Well, r squared then will equal 4 plus 0, which will make r2. Theta, again, if I draw this out, here's my point. Since I'm on the positive x-axis, I know that means that theta is 0. So by some strange coincidence, my cylindrical coordinate will actually also be 2, 0, negative 1. Another quick one here, 0, 4, 4. So in the xy plane, I'm up here. I know that theta is pi over 2. R squared is 0 plus 16, x squared plus y squared, which will mean that r is just 4. So my cylindrical coordinate would be 4 pi over 2, and z will just stay z. Z is 4. Okay. So that's just a look at changing coordinates. We can also represent equations of surfaces using cylindrical coordinates. For example, right here, this is a bit of a different, this is like a 3D grid. So like what I'll do here, and I missed it a little bit, but that's okay. R squared is equal to 4 minus z squared. Well, if you look at this, r squared we know is x squared plus y squared. If I rearrange that, I will get x squared plus y squared plus z squared equals 4, which is the unmistakable equation of a sphere with radius 2. So if I go at 2 on the y-axis, an x-axis, and z-axis, and in the negative z-axis, I would see something that looks like this. It's not a perfect drawing. It looks a bit distorted, but we would have a sphere. All right, what if I said r equals 2? If I set my axes and I say r equals 2, I go out 2 in both the x and y directions, because I understand r is measured in the xy plane. So if I confine myself to r being 2, and then I extend this, I extrude it into the z direction, I get a right circular cylinder. Now, this is sort of why it's called cylindrical coordinates. If I specify, I take that first coordinate, r, and just say r equals some number, what I get is a cylinder, a circular cylinder. Now, if I say something like theta equals pi over 4, and I'm not really going to use the 3D graph here because it's not going to show this well. I'm just going to draw another axis off here, and that'll be my y-axis. So theta is pi over 4. So that means I'm in the xy plane, and theta is pi over 4. So I come out here. That means I will get all the points on this ray. And I can, again, vary z, so I can extrude upwards. What I get in this instance is a plane, or more technically, it's a half plane, since we are considering r to be non-negative. And that would be the same regardless of the value of theta. I would get some sort of plane. Not specified here, if I took my third coordinate, z, and just said something like z equals 5, obviously that is simply a plane which is parallel to the xy coordinate plane. Here we have some equations which are in Cartesian form, and we want to change them to cylindrical equations to see what they look like. Now, of course, it helps if we understand what these are representing. Here, x squared plus y squared equals 4z. I can see that when z is 0, I will have the origin. And if I start thinking about this, as z changes, as z increases to 1, I will have a circle of radius 4. When z gets to be 2, I will have a circle whose radius is the square root of 8. I will have circles going up, but my other cross sections, I would have, for example, 4z equals x squared. So this is a paraboloid, a circular paraboloid. How do I change this to from a Cartesian equation to cylindrical? Well, again, I know that x squared plus y squared is equal to r squared. And there's really nothing I can do to simplify that. So I will say that r squared is equal to 4z. X squared plus y squared equals z squared. Well, again, this means that r squared is equal to z squared. Be careful here. This is not exactly the same as just saying r equals z, again, if we're thinking about the restriction on r. R squared equals z squared. This thing right here is a cone, a circular cone. If I limit this and were to say only r equals z would only be the top half of my cone. But if I stick to r squared equals z squared, or even write r equals plus or minus z, I will actually get the full cone, which is infinite in both directions. Okay, This last thing right here, x squared minus y squared equals 4. Well, x squared minus y squared equals 4. Even though that's not 1, I recognize I'm subtracting two quadratic terms, two squared terms, which means this in the xy plane would be a hyperbola opening in the x directions. I'm not going to worry too much about making this accurate. It'll look something like this. So since z is allowed to vary, what I would have in 3 space, again if I'm trying to visualize what this would look like, is this right here, and then I have to extend this up. I have to extrude it. And forgive me, these are not the easiest things in the world to draw. This extrusion of a hyperbola would just be called a hyperbolic cylinder. Anyway, though, what's the equation going to be? Now, I don't have x squared plus y squared, so I can't simply change it the way I did these. I need to think a little bit harder. X squared, well, x is r cos theta, so that would be r squared cos squared theta. Y is r sine theta, so I can square that. What do I get here? Well, it's not particularly pretty. I can factor out an r squared and be left with cos squared theta minus sine squared theta. This product is equal to 4. I can't do much with that. I can rewrite this as r squared times the cosine of 2 theta. But either way, it's not a pretty equation. I would just have to recognize or do the work in some fashion to figure out that that's a hyperbolic cylinder. All right, so those are the basics of cylindrical coordinates. What if I wanted to do spherical coordinates? Spherical coordinates are different concept than cylindrical coordinates. Spherical coordinates uses rho, theta, and phi. Phi, which may be written like this, or more like this, but they're both phi. They're used interchangeably. Rho, theta, and phi. So rho refers to the distance from the origin to whatever point I'm describing. So this length right here is rho. Theta is the same theta as in polar and cylindrical coordinates. It is the angle in the xy plane between the positive x-axis, and in this case it would be the projection of this vector onto the xy plane. And then there's the question of what is phi. Phi is the angle formed between the positive z-axis and this vector here. That's phi right there. Rho is the length, phi is the angle. This right here is theta, this distance is r. So if I look at that picture, if I think about that, I can actually establish the necessary relationships. First off, for restrictions, to have unique coordinates, I will allow rho only to be 0 or greater. Theta will still vary, as we said before. It will vary from 0 to 2 pi, but not including 2 pi. Phi only needs to vary from 0 to pi, including both endpoints. If I were to go past pi, you have to think in 3 dimensions here. If I come down, pi would take me all the way to the negative z-axis. If I go past that, I'm talking about breaking through the xz plane, going on the other side. Rather than doing it that way, it would be just as simple to actually allow theta to be a larger angle to get me onto that side of the plane. So phi only goes from 0 to pi. Conversions. X is equal to rho sine phi cos theta. Y is equal to rho sine phi sine theta. Z is equal to rho cos phi. And theta is the same theta we've been using. Rho, since it is the distance from the origin to whatever this point is, can be found by taking the square root of the sum of the squares of x, y, and z. Or just to say it, rho squared is x squared plus y squared plus z squared. Now we should think about why some of this works. Right here, if I'm looking at this, I see rho sine phi cos theta and rho sine phi sine theta are the conversions to get x and y from spherical coordinates. Now I think about that for a minute, and I realize in cylindrical and polar coordinates, x is r cos theta, y is r sine theta. So what I must conclude here, and what we can actually justify, is that r is, in fact, rho sine phi. If I look up my diagram right here, I can actually see this. So if I complete my rectangle up here, this is also r. And yeah, r is rho times the sine of phi. It's the hypotenuse times the sine of this angle. And then it makes sense why these x and y conversions hold. I can also see that z is rho cos phi because, again, if I'm looking in this same triangle, if I multiply the hypotenuse by the cosine of this angle, I will get the adjacent side, the z distance. And rho cos phi will tell me whether or not z needs to be positive or negative. If I need to go in the other direction, I remember the conversion. I remember the property that the tangent of theta is equal to y over x. The cosine of phi is z over rho, same way we justified it up here. And rho squared, as I said, is x squared plus y squared plus z squared. So let's look at changing some points, and then we'll look at some equations. I want to change the point 2 pi over 2 pi over 6 from spherical to Cartesian, which means I need to find the x, y, and z. So I know that x is rho sine phi cos theta. Now be careful here, you're just learning this. It might be helpful. Say it to yourself, write it down. Spherical coordinates are rho theta phi. If you switch up which one's theta, which one's phi, you're going to have a bad time. So, this is 2 times the sine of phi, which is this one, theta, phi, and rho. 2 times the sine of pi over 6 times the cosine of pi over 2. Well, I'll need the sine of pi over 6 anyhow in a moment. It's 1/2. But the cosine of pi over 2 is 0. So x is 0. What about y? Well, y will be rho sine phi sine theta, which means I will have 2 times the sine of pi over 6 times the sine of pi over 2, which is 2 times 1/2 times 1, which is 1. Z is rho cos phi, so that's 2 times the cosine of pi over 6, or 2 times the square root of 3 over 2. So my coordinate is 0, 1, square root of 3. Now make sure you're using this conversion. We do know that rho squared is x squared plus y squared plus z squared, but the problem with that is that equation is not going to tell you, even if you already know rho, x, and y, this equation won't tell you if z is positive or negative. You can reason it out. Take a look at example 11, we'll see it. I want to change this point from spherical to Cartesian coordinates. So x is rho times the sine of phi, which is 2 pi over 3, times the cosine of theta, 3 pi over 4. Well, that is 4 times the sine of 2 pi over 3 is the square root of 3 over 2. The cosine of 3 pi over 4 is negative root 2 over 2. If I multiply this out, the 4 will eliminate the two denominators, and I will have the negative square root of 6. For y, I will have 4 times the sine of 2 pi over 3 times the sine of 3 pi over 4, which is virtually the same thing. The only difference is I will have a positive square root of 2 over 2, which will then give me the positive square root of 6. When I go to find z, z is rho cos phi. So that will be 4 times the cosine of 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2. So my coordinate is negative square root 6, square root 6, negative 2. As I said a moment ago, in theory you could consider that rho squared is x squared plus y squared plus z squared, but where you'd run into trouble with that is you would have 16 is equal to 6 plus 6 plus z squared, which would mean then that 4 is equal to z squared. You have no idea whether that's a positive 2 or a negative 2. But if you're thinking in 3 dimensions, I know that phi is 2 pi over 3. So thinking in 3 dimensions, that means I'm up here, the positive z-axis, and I go down, down, down. Pi over 2 takes me to the xy plane. As soon as I go past that, I'm below the xy plane, where z is negative. So you could do it that way. I wouldn't necessarily encourage it. But z is most definitely negative. All right. Try one more conversion, and then we'll look at the equation conversion. I want to change this point. This time I'm going from Cartesian to spherical. So first I will find rho. Rho squared is the sum of the squares of each of these, which is 4 plus 4 times 3 plus 16 times 3, which is, let's see, that's 4 plus 12 plus 48, so that's 64. Which means rho is 8. I also need to find theta, and I need to find phi. Be careful when you're finding theta. We know that the tangent of theta is y over x, negative 2 square root 3 over negative 2, which is the square root of 3. Now before you jump in and say pi over 3, remember where these x's and y's would put you in space. Negative 2, negative 2 over the square root of 3. This puts me in the third quadrant. So theta here actually needs to be not pi over 6, excuse me, not pi over 3, but 4 pi over 3. That leaves me to find phi. The cosine of phi is z over rho, which is 4 square root 3 over 8, or square root 3 over 2. I have a positive z. Theta is acute, which makes sense. Or excuse me, not theta. Phi is acute, which makes sense. Phi is pi over 6. So my coordinate in spherical would be 8, 4 pi over 3, pi over 6. All right. Let's look at converting some equations. I want to change the Cartesian equation to a spherical equation. Now if I look at this equation, I see x squared plus y squared plus z squared minus 2z equals 0. X squared plus y squared plus z squared is a big clue that this is a sphere. But normally a sphere would equal some radius. Well, of course, since I have minus 2z right there, that means I could complete the square and figure out that I need to add 1. And it is a sphere of radius 1. We weren't specifically asked about that. We were asked to convert to a spherical equation. Well, x squared plus y squared plus z squared is rho squared. And from that, I'm subtracting 2z. Z, which is rho cos phi. So from this, I can factor out a phi and rewrite my equation thusly. Now, I could separate this. This is an equation that says phi is 0, or phi minus 2 says rho is 0, or rho minus 2 cos phi is 0. Well, I actually only need to write rho minus 2 cos phi equals 0, or rather rho equals 2 cos phi. The reason being, the point where rho is actually 0, well, that exists in this equation. Rho will equal 0 when phi is pi over 2. Now I want to change this spherical equation into a Cartesian equation. Rho is equal to 2 sine phi cos theta. Well, if that was rho squared, this would be a bit cleaner. And over here, I know that rho sine phi cos theta, that's x. So what I'm going to do is multiply in a rho on both sides. Rho squared will equal 2 rho sine phi cos theta. Rho squared is x squared plus y squared plus z squared. And what I have over here is 2x. So I can then convert this x squared minus 2x plus y squared plus z squared equals 0. Now technically I've already converted it. I had converted it here. But if I want to understand what this is, if I really want to justify that, I need to complete the square here. I know that this will come from x minus 1 squared if I add a 1 to both sides. So forgive me here, I'm doing this work more condensed than I probably should. If I added a 1 up here, I could add it here, and then I would have x minus 1 squared would equal 1. So I have a sphere of radius 1, which has been translated 1 unit in the positive x direction. If I wanted to change the spherical equation, rho equals 2 cosecant phi, into a Cartesian equation, well, we never really talked about the cosecant of phi, so we probably want to think about that in terms of sine and cosine. This is 2 over the sine of phi, which actually means that rho sine phi is equal to 2. Now, you could do some more math here to work things out. I'm going to be a bit clever. What did we say a few minutes ago? Rho sine phi is r. So this means that r is 2, which in Cartesian equation terms means that the square root of x squared plus y squared is equal to 2. Brain getting ahead of me. Or rather, x squared plus y squared equals 4. That's a 2. Sorry. Okay. So this is the equation of a cylinder of radius 2 with axis the z-axis. Again, I'm sure you could do this a bit differently, but That's how I'm sticking to it. In this example down here, I want to change r squared equals x squared plus y squared into an equation with rho. That's sort of a confusing ask, but what we're going for here is basically justifying the property we just used, that rho sine phi is in fact r. If I replace these with their spherical conversions, x is rho sine phi cos theta, y is rho sine phi sine theta, if I factor out rho squared sine squared phi, I have cos squared theta plus sine squared theta, which is 1. So I can then say that r squared is equal to rho squared sine squared phi. Now I can justify square rooting both of those sides because we're using the restrictions that r will always be greater than or equal to 0, as will rho, and phi ranges only from 0 to pi, meaning the sign will always be positive. So it makes sense to remove all the squares here and just say r equals rho sine phi. All right. The last bit here to wrap up, if we consider the graphs of some known equations and shapes, or really surfaces is the proper terminology, if we think about this in Cartesian, the equation of a cylinder would be, for instance, x squared plus y squared equals, I'll use k squared to represent the radius. I can't use r, since we're about to use r to mean something else. Well, in cylindrical, I have an r. This is r squared, so all I would need to say is r equals k. In spherical, we know that r is rho sine phi. So rho sine phi is equal to k is the equation of a cylinder, or at least a right circular cylinder with axis the z-axis. How about a sphere? Sphere has equation x squared plus y squared plus z squared equals k squared. In cylindrical, that would be r squared plus z squared equals k squared. In spherical, x squared plus y squared plus z squared is just rho squared. Rho squared equals k squared, so here I could just say rho equals k. Again, that's why it's called spherical. If I take that first coordinate and set it to a constant, I'm describing a sphere. How about a cone? Well, a cone is z squared equals x squared plus y squared, which, as we said before, if you were to actually say z equals k, technically that would be a half cone because we're restricting I'm sorry, not z equals k, z equals r. This is r. X squared plus y squared is r squared, so z squared equals r squared, so then we would have z equals r. Sorry. So that would be a half cone if we're restricting r to be positive only. In spherical coordinates, what would I have for a cone? Well, it's not especially pretty. I'm going to write it off to the side here. I would have rho squared cos squared phi is equal to x squared plus y squared, we know is r squared. So if I am a little bit clever, then I can get this. Rho squared cos squared phi equals rho squared sine squared phi. Got lost with myself for a second there. What this would lead to is cos phi equals sine phi. Or rather, cos phi is the positive or negative of sine phi. That's actually a little misleading. This would give me both napes of a cone, but this is specifically a cone that forms a 45-degree angle to the z-axis. More generally, in spherical coordinates, I can describe one nape of a cone by saying phi is equal to some constant, which I will call A, or angle. Let me explain that a bit more. Think about it. If I'm in 3 space and I tell you phi equals pi over 3, then that means I come down pi over 3 from the z-axis. Since I haven't said anything about rho or theta, that means they are allowed to vary, which means I can go anywhere along this segment and I can rotate anywhere around the z-axis, which would give me one nape of my cone. For a plane, of course, there are many planes I could write, but for example, if I said z equals k, in cylindrical, that would also be z equals k. And in spherical, that would be rho cos phi is k. Again, that's not all planes. If I had x equals a constant, then I would, of course, have significantly different equations here. But that's the general idea.